Question is the steady state current response of a series RLC circuit to a sinusoidal input of 10 sine of omega t volts is given by 5 sine of omega t minus 30 degrees amps. Its current response to an input of 10 cos of omega t plus 30 degrees volts will be. Here see, from the given data we can obtain the impedance of an RLC network, which is equals to voltage divided by current, that is 10 angle of 0 divided by 5 angle of minus 30 degrees, which is equals to 2 at the angle of 30 degrees, that is the impedance. But the voltage and currents in the Z expression involved in the form of sine. But in the next case, the input is in the form of 10 cos of omega t plus 30 degrees. So we can express it in the equivalent sine form by advancing it by 90 degrees, that is 10 sine of omega t plus 30 degrees plus 90 degrees, which is equals to 10 sine of omega t plus 120 degrees. For this particular input we have to calculate the current, that is I equals to 10 at the angle of 120 degrees divided by 2 at the angle of 30 degrees, that is 5 at the angle of 90 degrees. Now we can write this as 5 sine of omega t plus 90 degrees, because in the above current expression the voltage is in the sine form as well as the impedance which we calculated from the Z expression is also in the form of sine expression. So it is equivalent to 5 cos of omega t amps, which is option D is correct.
The given differential equation is dy by dx plus p of x into y is equals to xy cube. And also its solution is given as y square into 1 plus c into e power x square is equals to 1. Now we have to find the value of p of x. In order to find the value of p of x, first of all, we have to convert the given differential equation into first order differential equation. Now, in order to convert that, we have to divide the given differential equation by y cube. So, if we divide it by y cube, we'll obtain y power minus 3 into dy by dx plus y power minus 2 into dy by into p of x is equals to x. Now, again, in order to convert it into first order differential equation, what we do is let us consider y power minus 2 into dy by dx as some z. Now, if we differentiate, we'll get it as minus 2 into y power minus 3 into dy by dx is equals to dz by dx. Now, this can be written as y power minus 3 equals to minus half into dz by dx. Now, let us substitute these values of y power minus 2 and y power minus 3 in the differential equation. So, it will be y power minus 3 is nothing but minus 1 by 2 into minus 1 by 2 into dz by dx, and the value of p of x will be as it is, and y power minus 2 is nothing but z is equals to some x. Now this can be written as dz by dx minus 2zx is equals to minus 2x. Now clearly it is in the form of a first order differential equation whose integrating factor will be e power minus p of x dx. Now here this is p of x. Now here clearly this p of x must be either x or minus x. The reason is it is given as e power minus x square. So p of x integrating factor will be e power minus x square if and only if this p of x is x or minus x. So let us take x. Let p of x is equals to x. Then the integrating factor will be e power minus x square. Now let us see the general solution. General solution will be nothing but y into integrating factor, which is e power minus x square, is equals to integration of integrating factor into q of x, which is nothing but minus 2x dx. If I integrate this, it will be y into e power minus x square, that is equals to e power minus x square plus some c. If we simplify, we'll get the given solution of the equation. That means the integrating factor is e power minus x square. So p of x must be always x, which is nothing but option C.
Here question is, we need to specify what kind of filtering action performed by the given network. Here the reactance of a capacitance is given as Xc equals to 1 by j omega c, means omega tends to 0 means X reactance of capacitance tends to infinite, whereas omega tends to infinite means reactance of capacitance tends to 0. Here in the first case where omega tends to 0, capacitor acts as a open circuit. Whereas in the second case where omega tends to infinite, capacitor acts as a short circuit. That is, when omega equals to 0, V out equals to V in, whereas when omega equals to infinite, V out equals to 0. If we plot output voltage as a function of frequency, at omega equals to 0, V in, at omega equals to infinite, it is 0. Means as frequency increases, the output decreases. Maybe it's not an exact shape, but the output increases as frequency increases. That is the function of the low pass filter, which is option A is correct. Question is, with the usual notations, we need to derive the relationship between the given parameters alpha, beta, f alpha, f beta and f suffix t. Here alpha is common base current gain, where beta is common emitter short circuit current gain, and f alpha is the upper cutoff frequency of common base amplifier, f beta is the upper cutoff frequency of common emitter amplifier, and ft is the short circuit current gain of common emitter amplifier. We know the relationship between ft and f beta is given as beta into f beta. So again ft equals to f alpha equals to beta plus 1 into f beta. From this we can derive the relationship between the ft and f alpha as ft equals to alpha into f alpha. From this the answer is option A is correct.